Hello and welcome back. Today we're finishing out Chapter 4 with Section 4.6, Inequalities with Real Numbers. So now our domain, now that we're out of Chapters 2 and 3, is expanded to the entire set of real numbers. So we'll start by going over a quick sketch of a graph for a solution and also how to go to an interval for a set of numbers. So we'll start with the inequality x is strictly less than 1 5/10. So we'll start with our graph. So 1 5/10 is between 1 and 2 on the real number line. And then we'll just go a few in either direction. So 1 5/10, as I mentioned, is between 1 and 2 on the real number line. So our border is about here where I'm dropping the pen. And if we use one test point to the left, one test point to the right, one of them will make sense, one of them won't. -4 is less than 1 5/10, makes sense. 5 is less than 1 5/10, does not make sense. Now back in our days where we kept integers only, we would keep then just the 1, the 0, the -1, the -2, and so on. However, now that our domain is in the set of reals, not only do I get to keep the 1, but I can keep 1.49999992. I can keep 0.11. I can keep opposite of pi. I can keep all of these rational and irrational numbers in between these points. So what I'm going to do is shade everything from the 1 5/10, and in this case to the left, because not only are we keeping those integers, but all of the rationals and irrationals in between them. Then instead of a dot, we use either a parenthesis or a bracket, depending on if we get to keep the boundary or don't get to keep the boundary. If I tried 1 5/10, 1 5/10 is strictly less than 1 5/10, does not work. So we can get close to it, we just can't use it. If we cannot use it, it gets a nice round parenthesis, and you just lean the parenthesis in the direction that you just shaded. So that's what our graph would look like. As far as interval notation then, how far left you can go, comma, how far right you can go. I can never reach negative infinity. If you think you found it, subtract 1,000,000 from that, and you could keep doing that forever. Again, we talked about a minute ago that 1 5/10 will not work. We can approach it, we can't reach it, so that will also get a parenthesis. So notice on this, we don't have a set theory representation. We now have an interval representation of the set of numbers that work. All right, so we'll also take a look at, let's try -1 4/10 is less than or equal to x, which is strictly less than 3. So again, I'll start with my graph and then I'll go to interval notation as well. So I'll put 3 about here. So we want our x's to be between these two values. So Here is the -1 and 4/10. Notice it's between the -2 and the -1, not between the -1 and the 0. And we're a little bit closer to the -1 than we are to the -2. And of course our 3 on the other side. Again, if we were to be working just in the integer domain, I'd keep the -1, the 0, the 1, the 2, and would not be able to keep the 3. But real number domain, we get to keep all these nice, neat, pretty rationals and irrationals in between. So I'll go all the way out to the -1 and 4/10 and all the way up to the 3. We are allowed to keep the -1 and 4/10. We have this or equals, so the -1 and 4/10 will get a nice square bracket leaning in the direction we shaded. The 3 gets a nice round parenthesis since we had strict inequality on the 3. And our interval for that looks very much like what our graph looks like. Bracket if we're allowed to use it, parenthesis if we're allowed to just get close to it. Okay, so then that lets us do a little bit of practice with some simple solving inequalities. Again, with a real number domain, so make sure you're watching for that on quizzes and tests. Which domain are we working with on that problem? So this first one, I'd add 2 to both sides of the inequality, adding and subtracting. We can do that all we want. We do not flip the inequality symbol via adding and subtracting. And then we'll just multiply both sides, but it's by a positive. If you multiply by a positive, the inequality stays put. So x is greater than or equal to positive 3/4. Okay, so 3/4 is between the 0 and the 1. Closer, of course, to the 1. And testing 1 from each side, seeing which one works. 0 greater than or equal to positive 3/4 does not work, but 5 greater than or equal to 3/4 does. So we will shade the side with the 5. Arrow on the end, since we can keep going that way forever. We have the or equals, so we will include that with a bracket. So then that is our graph. If they ask for an interval, 3/4 is our lower bound, positive infinity our upper bound. We still can't reach infinity, so even though this has an or equals, we can never get to a biggest number. If you think you found it, multiply it by 23 trillion. If you think that's it, add 1 to that. And you could keep doing that forever. So we always approach infinity. We don't reach infinity. All right. A couple more of these. I'll play with some of our absolute value friends. There we go. Okay, so the next one, we get a little practice in with our sign work. So we'll do 15 is strictly greater than -3x plus 2. We want the x by itself, so I'll subtract 2 on both sides to start this off. Add or subtract all you want. That won't flip the inequality symbol. Next, we'll multiply both sides by -1/3. And that's when the alarm bells should be clanging in your head. If you're multiplying both sides by a negative value, that is the thing that will flip our inequality symbol around. So it was a greater than, now this is a less than. So -13/3 is strictly less than x. Negative or a positive is negative. 3 will go into 13 4 times with 1 left over. So -4 1/3 is strictly less than x. After that, all the graphing is the same as what we have been doing. So we put our scale on there. So -4 1/3 is between the -4 and -5 here. -5 and -4, I should say it left to right. So here is -4 and -4 and 1/3, right about there on our number line. So -4 1/3 is less than -9 is false. Think of a $sign in front of it. You're better off at -$4 than -9 in your account. -4 1/3 less than -1, or +2 would be over here as well. +7 over here. Negative less than a positive does make sense, so we're going to shade in the direction of the positives, so to the right. Strict inequality, so the -4 1/3 will get a parenthesis leaning that way instead of a bracket leaning that way. So our interval, -4 1/3, is the furthest to the left that we can go, and we can go to the right forever. In other words, we can approach infinity. So that would be our interval for that one. So one more of these, the double inequality, -2 less than or equal to 3x minus 1, which is strictly less than +11. So the first thing I would move, if this were my inequality, is I would add 1 to both sides. This inequality, I would add 1 to both sides, so that's exactly what we'll do. We'll add 1 to all 3 pieces. So -1 is less than or equal to 3x, which is less than 12. And we'll divide all 3 pieces by 3, equivalently multiply by 1/3. And as long as we're multiplying by a positive, the inequality symbol stays parked. So -1/3 is less than or equal to x, which is less than 4. All right, got that in there a little tight, so we'll just do our sketch below. Okay, so we'll start at maybe -2, -1, 0, 1, 2, 3, 4, and 5. So the x, notice, is in the middle of those two. So -1/3, not quite to the halfway point between -1 and 0. And shading, moving towards the 4. 4, we should start moving down. So we keep that middle section. The 4, strict inequality, we can only get close. That will get a parenthesis leaning towards where we shaded. -1/3, we have the or equals. That we keep. So that got a nice neat bracket on it. So our solution in interval notation, -1/3, which has a bracket, up to but not including 4, so the 4 gets a parenthesis. Okay, so we'll do a little bit with the ands and ors and absolute values. There we go. We'll start with an and. We'll have 5x plus 2 is strictly greater than 9, and 2 is strictly less than x minus 4. So we just solve each one of these. The first inequality, I'll subtract 2 on both sides. So 5x is strictly greater than 7. Multiply both sides by a fifth or divide by 5. Those are equivalent operations. 1 times x is x. 7/5. 5 goes into 7 once with 2 left over. This is an and, so we will intersect that with our solution to the other one. This other one we'll solve a little bit faster. We'll add 4 to both sides. So 6 is less than x. Okay, so these ands and ors, remember we're going to have basically 3 graphs going, one for the first, one for the second, and one for the either and or, the intersection or union. Okay, so we'll start with x is greater than 1 and 2/5. So here's 1 and 2/5. 2/5 is a little less than half. So right about there. And I want x's that are greater than that. So for example, 8 is greater than 1 and 2/5. So I'll shade towards the 8. Strict inequality, so we'll get a parenthesis going there. Next up, we'll graph 6 is less than x. So now it's 6 that's in the hot seat. I want 6 to be less than x. We test each side out. So if I try out maybe the 1, 6 is less than 1 does not make sense, but 6 is less than 8 does make sense, so I'll shade in the direction of the 8 again. Strict inequality on this one as well, another parenthesis. And I'll put the label on the side for what that one was. That was 6 is less than x. Ooh, baby is awake. All right, so what we do next depends on if this is a union or an intersection. This one was an intersection, an and problem. Remember our work on intersections. If it's in the intersection, it has to work for both. So clearly everything back here doesn't work for anybody. That's going to stay blank. In the middle here, it works for one but not the other. That would be fine if this were an or problem, but it's an and problem, so I don't get to keep this on my final answer. It's only the things over here that worked for both. So that's what I'll keep in my final answer. So the 6 and everything to the right. So 6 approaching infinity. All right, so a union problem up next. All right, so we'll do 11 is less than or equal to x minus 5 together with 17 is greater than x plus 6. Okay, so not too much difficulty in solving those. So the first one, I'll add 5 to both sides. So 16 is less than or equal to x. This one we're going to connect them with an or, which it will be a union. The next one we will subtract 6 on both sides. So 11 is strictly greater than x. So individually, the graphs come together pretty quickly. So this first one is for the 16 is less than or equal to x. So here's our 16. If I plug in a number to the left side, say a 10, 16 less than or equal to 10 doesn't work. 16 less than or equal to 18 does work. Shade towards the 18. We had the OR equals, so the 16 will get a bracket on it. So next line, same deal. Get my labels going here. And this will be for the 11 is strictly greater than X. So my cut is here at the 11. If I try out a number on the left, 11 is greater than 9. That does work. If I try out a number on the right, 11 is greater than 15, does not work. So I want the left side. Strict inequality, so the 11 gets a parenthesis. Now what we do next with it really depends on, try to stay consistent, went down to 9 both times. What we do next with it depends on if it's an and or an or. This one is an or, a union. Or says if it works for one or the other or both, we're happy and we will keep it in our final answer. So the first chunk of the graph, notice I have sort of 2 cuts, made 3 sections total. It came through for the second graph, so we would keep this section. The middle missed on both of them. We'll skip the middle, and the far right worked for the first one, but not the second. As long as this is an or, a union problem, that's okay, and we'll keep it. So I keep everything from 11 to the left. Not the 11 itself, but close to 11, 10.999999996. And everything from 16 inclusive to the right. Tell the reader I get to keep the 16. Notice it has a nice pretty bracket on it as opposed to the nice rounded parenthesis. Our interval is going to look a little bit different, but it should look somewhat familiar to what we did in our set theory days when we had the gap. So the first piece of the number line that we get to keep, go to the left forever. To the right we can go all the way up to but not include the 11. And then we just put our union symbol in the middle. Next we pick it up at 16. We include the 16, so that one gets a bracket. And we go to the right forever. We can approach infinity. So there's our unions and intersections. So next we had our absolute values. And just like before, we're going to sort of do the let line, pretend that we had an equation. So we're going to solve absolute value of the sum of 3x and 2 is less than or equal to positive 9. We'll let this temporarily be an equation. Absolute value is by itself. If it's not, fix that first and then move on from there. Absolute value equals to a positive is 2 possible solutions. It might be worth negative 9, union that up with the possibility that it was worth positive 9. And we'll solve those two. So first one, I'm subtracting 2 on both sides. So 3x is equal to negative 11. We'll multiply both sides by a third. So 1 times x is x, negative 11 thirds. 3 would go into 11 3 times with 2 left over. Second one, start by subtracting 2 on both sides. 3x plus 0 is 3x. 9 minus 2 is 7. Third of both sides. 1 times x is x. 3 would go into 7 twice with 1 left over. All right, I'm going to continue this on the next page. I'll just copy over the relevant bits of information. So absolute value of 3x plus 2 less than or equal to 9. So that was our original inequality, and then our two cuts into the number line, x is negative 3 2/3. Union that up with x is 2 1/3. So we've once again made two cuts to our number line, which will make 3 separate sections, and it's just a question of which section or sections do we want to have. All right, so 5. Okay, a little imagination and we'll pretend those are nice and neat and evenly spaced. When we're graphing in just one number line, spacing doesn't have to be as precise as it does when we need the 2D graphs. Okay, so our two cuts, negative 3 2/3, so negative 3 and a little extra, so we're between negative 4 and negative 3. And positive 2 1/3, between positive 2 and positive 3. And we just identify some test points. If they work, we keep it. If they don't work, we don't keep it. So we'll test out x equals negative, say 10. In the middle, x equals 0 is a nice, easy to work with number, and something to the right of 2 1/3, we'll try, let's try the 4. Okay, so 3 test points. We plug them into the original inequality and see if they work. So absolute value of 3 times negative 10 plus 2, close the absolute value, and we want to know, is that less than or equal to positive 9? So negative 30 plus 2 inside the absolute value, possibly less than or equal to 9. Absolute value negative 28, possibly less than or equal to 9. 28 less than or equal to positive 9 is false. We don't want that far left section. So then we try the middle with the 0. Plug it into the original inequality. Absolute value of 0 plus 2, possibly less than or equal to 9. Absolute value of 2, possibly less than or equal to 9. 2 less than or equal to 9. That does make sense. So we definitely want the middle chunk of the graph. And finally, we test out the 4. So answer the value of 14, possibly less than or equal to 9. 14 less than or equal to 9 is false. We don't want the last section. So we want everything between the negative 3 2/3. So a little bit past the halfway point of the 4, up to the 2 1/3. A little less than the halfway point for that guy. So we want this stuff in the middle. Brackets on both of them because we have the or equals. So in this one, we would keep from negative 3 2/3 inclusive up to 2 1/3 also inclusive. All right. So next one, play with absolute value of 2x plus 1 is greater than or equal to 4. Again, we use our let line, pretend we have an equation. Absolute value is by itself, positive on the other side, so I'll set up 2 equations to make. So 2x plus 1 might be worth negative 4, union that up with 2x plus 1 possibly being positive 4. So we're just solving 2 equations. They're temporarily equations. So 2x is worth negative 5. Multiply both sides by a half. That's equivalent to divided by 2. 1 times x is x. Positive by a negative is a negative. 2 goes into 5 twice with 1 left over. And we solve our next guy the same way. Subtract 1 on both sides. So 2x is worth 3. Multiply both sides by half, equivalent to dividing by 2. So positive by a positive is positive. 2 goes into 3 one time with 1 left over. All right. So let's see. Yeah, we'll just get our relevant stuff onto the next page. So negative 2 1/3, positive 1/3. And our original inequality, absolute value of 2x plus 1 is at least 4. Okay, so again, just our single number line. So negative 2 and a little extra. So we're between negative 3 and negative 2, 1 and 1/2, exactly halfway between the 1 and the 2. So 3 sections of the graph, 1 number per section. So maybe x is negative 4, x is 0, and x is 2. Plug them into the inequality and see if they work. Absolute value of 2 by negative 4 plus 1, close it up, is that greater than or equal to 4? So we have negative 8 plus 1, negative 7, absolute value of negative 7, possibly at least 4. 7 greater than or equal to 4 is true. So we want the far left part of our graph. In the middle, absolute value of 2 by 0 plus 1, possibly at least 4. 2 by 0, 0, 0 plus 1 is 1, absolute value of 1, possibly at least 4. 1 is not greater than or equal to 4. We don't want the middle part. And finally, trying out the 2. So 4 and 1 is 5, absolute value of 5, possibly at least 4. 5 greater than or equal to 4 is true. We want the last part of our graph as well. So I want everything from negative 2 1/3 to the left. I want everything from 1 1/2 to the right. We had our or equals, so brackets on both of those. So our solution set, negative infinity on the left, up to and including the negative 2 1/3. Union that up with the next section, 1 1/2, approaching infinity. Okay, so our next one, absolute value of the difference of x and 5, strictly greater than negative 6. So we use our let line, let absolute value of x minus 5 temporarily equal negative 6. Absolute value is by itself. If it's not, fix that. Then we look at how many ways can this happen. Absolute value equals a negative is not possible. All that means at the moment is that I have no cuts to the real number line. So it means either I'll keep all of the real number line or none of the real number line. So we'll just test out 0. If it works, we'll keep the whole thing. If it doesn't work, we'll throw the whole thing away. So absolute value of 0 minus 5, possibly greater than negative 6. 0 minus 5 is negative 5. Absolute value of negative 5, possibly greater than negative 6. Absolute value of negative 5 is positive 5. Positive greater than a negative is, of course, a true statement. So on this one, we keep it all. So shade that whole number line, arrows both directions, and we'll go from negative infinity to infinity. Keep the whole thing. All right, so one more involving the negatives, and that will give you enough to get section 4.6 done, the last of chapter 4. Absolute value of the sum of 3x and 2 is less than or equal to a negative 1. So we start with our let line, let this temporarily be an equation. Absolute value is alone. Then we ask how many ways it can happen. There's no way that this can happen, an absolute value equal to a negative.